Hi everyone, welcome back to Physics 2. We're going to continue talking about current, but we're going to talk about an aspect of current basically as it's flowing through a material. So materials are going to present a resistance to current, right? Current is the flow of moving charges. So if moving charges are flowing through a material, you can imagine that they're going to be banging against atoms of that material. They're going to be banging against themselves, and it's going to take some effort or some energy to propel them through a material. And resistivity and resistance are measures of that opposition to the current, okay? So we saw that current only exists in a wire. We only get the charges in that wire to start moving if we apply a potential difference between the ends of the wire. And why is that? Because potential difference, V, gives charged particles Q the energy to start moving. So the only way we can give them energy is by applying a potential difference. So we also know that this potential V that we apply will create an electric field, right? This V will create an electric field E. So if we apply a potential over a certain distance D, an electric field is created. And thinking of it in terms of force, we know that the force that a particle Q feels in an electric field is QE. So that's kind of setting us up for our discussion. We're looking at what happens to a wire when we apply a particular potential difference to it, and specifically what happens to the current in that wire. So to help us understand the behavior of the current, we're going to look at three relationships. The first relationship is going to be how the potential difference and the electric field are related. And we kind of already know that, but we're going to look at it in the context of a wire instead of like out in outer space or in vacuum. Number two, we're going to look at how the current is related to the electric field in a wire. And finally, how the potential and the current are related. Okay, so we're going to look at these three relationships. And like I said before, the context of this discussion is we're talking about a wire, okay, made of some kind of conducting material, and we're applying a potential to the ends of the wire. So if we're applying a higher potential to that side, that means we're hooking up that wire to the positive side of the battery, and then we're hooking up this side of the wire to the negative side of the battery, okay? So to answer the first question, let's consider this wire. It has a cross-sectional area of A length of L, and if we apply this potential difference V, we're going to get an electric field inside, okay? And what is that electric field? Well, we kind of looked at this last chapter, right? That electric field is V over L, okay? We looked at it through dimensional analysis. We saw that the electric field can also be expressed in units of volts per meter, okay, which is a potential difference over a distance. So that is exactly what we have right here. And we can also see this through our equation for potential of an electric field, right? It was minus ED cosine theta. So if cosine theta is 0 or 1, if cosine theta is 0 or 1, meaning, it's negative 1 or 1. I'm getting my numbers confused, right? If cosine theta is negative 1 or 1, then we are getting the same equation back right here. Okay, so we're still talking about the same potential. The potential applied across a distance D is going to set up an electric field, and those charges are going to feel that electric field and feel a force and start moving in the direction of the field if they're positive charges. And we also know how are electric fields related to potential? Well, they always point towards regions of lower potential, right? So it makes sense that the electric field will point in this way. So electric field and potential, we saw the relationship, V over D, or if we want to talk about it in terms of V is ED, okay? So that means that if we were to apply a potential of 1.5 volts, like from a AA battery, then the electric field that we would get would depend on how far we are connecting those potential points from the battery. So the length in which the electrons or the positively charged particles have to travel. And so that can give us the electric field setup inside the wire, which we're going to assume to be uniform. So for example, if we have 1.5 volts and the wire is 10 centimeters, then that would set up an electric field in that wire of 15 volts per meter. So to look at the second relationship, right, we looked at how E and V related. The second relationship, we don't really have anything to go off of except for experimental results. And experiments have been done to show that this is the relationship between current and electric field. So we just kind of have to accept that. Here is the relationship between current and electric field. The current is related to the electric field times the cross-sectional area of the wire divided by this guy, who is rho. And this is the resistivity of the material that the wire is made out of. Okay, so this resistivity value is a standard value, one for each type of material, and these are values that are experimentally determined. So rho depends on the material, okay? We don't know the value unless we do lots of measurements on it and figure it out. So these are tabulated values. And what rho tells us is how well or how poorly this material inhibits the flow of charge, okay? So how well it resists, right? It's the resistivity value, so how well it resists current or the flow of charge, right? So if the resistivity is high, then there is a lot of resistance to current, okay? If the resistivity is low, there is low resistance to current. And that makes sense if you look at the equation up here. I'll rewrite it over here. Electric field area divided by rho, right? There's an inverse relationship between current and resistivity. So increasing rho would decrease current, and decreasing rho would increase current. What is the units of rho? The units of rho are ohm meters. Okay? The units of rho are ohm meters. What is an ohm? An ohm is just short for a volt over an amp. Okay? So if we take a look at these units up here for that equation, electric field is volt over meter, area is meters squared, and then resistivity is going to be, we can solve for that, right? This is amps, this is resistivity. So if we solve for resistivity, we basically exchange places with I and rho. The units of resistivity are going to be voltmeters times meters squared over amps, which gives us a voltmeter over amp. We call this volt amp an ohm, which leaves us with ohm meters. Okay, which is what we have right here. So the resistivity units is ohm meters, and we've defined a new quantity, which is a volt over an amp, isn't called an ohm. And we'll be talking about ohms a lot. Ohms is the unit of resistance. So we'll get to what resistance is, but we're still talking about resistivity, right? Resistivity is a material property. It also has a temperature dependence, but we're not going to worry too much. So there is a temperature dependence, but we'll be mainly talking about room temperature. So let's look at some typical values. So for copper, which is a conductor, right? It's a conductor, meaning it conducts electrons very easily. So it should have a low resistivity, and it certainly does. Rubber is not a good conductor. It's an insulator, right? It does not like electrons penetrating its material. So it's going to have a very high resistivity, and certainly it does. It's 10 to the 13. Here's a table of some typical values, okay? So you can see this table is showing you that no matter the dimensions of the aluminum, its resistivity is 2.733 times 10 to the minus 8, right? These are material parameters, so they're constant for anything that's made of that material. So to look at the third relationship, okay, the third relationship, we were comparing basically I and V. All right. Let's take the equation we didn't derive it. We just kind of looked at it that we just learned, right? The relationship between I and electric field. And let's make a substitution since we know that the electric field is related to the potential. So let's substitute this for E, right? E is V over the distance, L, the length of the conductor. Let's make that substitution. And then let's couple all of these constants together, right? These are all constants. This is the cross-sectional area of the wire. This is the length of the wire. And then this is that material parameter resistivity. So what you can see is that the current is proportional to the potential by this group of constants, okay? If we rearrange it and put V over here on the left-hand side and I on the right-hand side, well, then that becomes rho L over A, okay? It's just mainly rearranging some algebra. And what we're gonna do is we're gonna call this quantity here R, resistance of the wire. And so this is a proportionality equation, right? If I put some potential V on a wire, then this amount of current is going to come out of that wire, and that amount of current is going to depend on the resistance of the wire. And the resistance of the wire, well, it depends on the resistivity of the material, the length of the wire, and the cross-sectional area of the wire. Okay, so this is a lot like we saw that Q equals CV, right? The amount of charge that appears on the plates of a capacitor depends on the amount of potential we provide, and it depends on what that capacitor's geometry is. Epsilon naught A over D, right? That was C. So we have another proportionality relationship. Now, instead of talking about capacitors, we're talking about current through wires, okay? Moving charges through a wire. So here's the resistance, right? Resistance is defined as the resistivity of the material times the length of that wire divided by the cross-sectional area of the wire. And that proportionality between, right, the relationship between V and I, it's given by V equals IR, where R is right up here. And V equals IR, this is also called Ohm's law. Okay, Ohm's law tells us that it's a simple linear relationship between potential and current. So if I apply a potential V to a wire, then I'm going to get this amount of current, V over R, in the wire. Okay? So the amount of potential I apply is scaled by R, and that tells me how much current I get. So that's exactly what this statement says, right? The potential difference that is required to produce a current I in the wire is proportional to I and R. So what it also tells us, what V equals IR also tells us, is that the resistance of the wire depends on the resistivity, or not V equals IR, sorry, that's R equals rho L over A. What that equation tells us is that the resistivity of the material, well, it depends on the resistance of the material depends on the resistivity, the length, and the area, cross-sectional area of the wire. So the units of resistance, okay, is going to end up being just the ohm. Okay, it's just ohms. Just ohms. And that's because when we plug in, let's write resistance up here. When we plug in all of our values of units, right, we have ohm meters times meters for length divided by meters squared for area. We get these meters all canceling and we're left with just ohms. So the resistance units is ohms. And an ohm is a volt per amp, right? Because we also know that V equals IR. In other words, R equals V over I, which is a volt per amp, right? Which is an ohm. So that's kind of how all these units are related to each other. This is the symbol for a resistor when we are starting to work with circuits. So the symbol of a resistor is like a jagged line. And that's because resistors were initially used as like heaters. So when you pass current through something, it heats up. It gets warm, right? Those electrons are bumping into the atoms of the material that they're flowing through. And those interactions generate heat. So that's like when you see an old school heater and you see like the red heating element, and it's hot, right? And then there's a fan behind it blowing the hot air. That red heating element is just, it's just a resistor that generates a lot of heat when you're passing current. So that red glow is there because you have these electrons in the current bumping into the atoms in that material, and that, constant hitting each other generates heat. So this V equals IR, right? Ohm's law. I told you that's Ohm's law. This is not always true for materials, okay? This is true for a certain set of materials that we call ohmic materials. All right, so ohmic materials will have this behavior. If you apply a potential V, you get an I out of it. So if you apply 2V, you get 2I. If you apply 3V, you get 3I, right? It's proportional. But there's some materials that are not ohmic, and that means that R isn't constant at all, right? If you apply a small V, you'll get a particular R. If you apply a large V, you get a totally different R. So in other words, ohmic materials would show up, if you were plotting V and I, would show up as a straight line. And non-ohmic materials, if you were plotting V against I, you would get maybe some curvature or something. Okay, you would get like an exponential function maybe. That was like a really bad one. You would get something like that, or even something like that. So that's the difference between ohmic and non-ohmic. So let's do this example together. In this example, we have a 10-meter long wire with a radius of 2 millimeters. So we're starting off with the wire, okay? The dimensions are obviously not to scale. And the resistance of that wire is 50 ohms. The question is, if we stretch this wire to 10 times its original length, what will be the new resistance? So you may be inclined to write down the equation for resistance, which is rho L over A, and noting that increasing L would increase the resistance, right? But by how much? Is it simply just by 10? Well, the answer is no, and here's why. When you take your original sized wire, okay, and you stretch it out, well, that's not stretching it. It looks like I can't stretch it. I can't stretch it without destroying the aspect ratio, right? You stretch it out. What else happens to the wire? You start losing your cross-sectional area, right? Your cross-sectional area actually starts to decrease as you increase the length. Think of it as a can of Play-Doh, right? You empty out the can of Play-Doh and it's like a little short, squat cylinder. And then you roll that Play-Doh out into a snake, and the length of the Play-Doh changes. It increases, obviously, right? If you're rolling it out as a snake, the cross-sectional area decreases. But by how much? We need to figure that out. The constraint that tells us how much everything changes is the fact that the volume remains constant. Okay, so you need to keep that in mind. You need to have this constraint in mind in order to properly figure out this relationship here. Okay, so let's examine it more. What does it mean that the volume remains constant? That means that the volume of wire 1 is going to equal the volume of wire 2. And so what is the volume of wire 1? It's the cross-sectional area A1 times the length, which would equal the cross-sectional area A2 times the new length. And we know the relationship between L1 and L2. We were given that. So we can kind of put that in here. And that is 10 times L1, right? L2 is 10 times L1 because we're increasing the length by 10 times its original length. And what I see is those L1s cancel off, and that A1 is going to be 10 times A2, okay? In other words, A2, if I divide by A2 and divide by A1 to switch sides, A2 is going to be equal to 1/10 of A1, right? Because I got 1 over A1 on the left, 1 over A1 on the right. So in order to express it in terms of not a fraction for A1 and A2, the constant proportionality becomes 1/10. So, and this makes sense, right? Because as you roll out the Play-Doh, the cross-sectional area decreases. So the new cross-sectional area A2 of the longer but thinner wire is going to be smaller than the original area. So that's why we are multiplying by 1/10 to make that original area smaller. So let's see how now that gets incorporated into our resistance relationship. So what we're going to do is we're going to compare the resistance of the first wire to the resistance of the second wire. So the resistance of the first wire is rho L1 over A1. And the resistance of the second wire is rho L2 over A2. And if we take a look at the ratio of R2 to R1, we're basically going to plug in all of our values. Rho L2 over A2 times, I'm multiplying by the reciprocal here, A1 rho L1. I'm going to plug in the relationships that I know for area and for length, right? The one for length is the length increases by a factor of 10. So when I plug in those relationships, I'm going to get some cancellations. Oh, there's a row here that's missing. And I get basically 10 divided by 1/10, right? That brings the 10 upstairs, making it 100. So what I have is that my ratio of R2 to R1 is 100. So if I move that R1 over, it'll be a lot easier to read that relationship, right? Bring the R1 to this side with the 100. R2, so the resistance of the second wire, the longer one and the skinnier one, is going to be 100 times the original resistance of 50. So in other words, R2 is going to equal 100 times 50, which is 5,000 ohms. Okay, so this was a tricky relationship problem. because we had some constraints here, and the constraints weren't exactly spelled out for us, right? We had to use this relationship here, the fact that the volumes are constant, in order to truly figure out by what factor the resistance increased, okay? So that constraint allowed us to create this second equation with A2 and A1. Plugging in this known as well allowed us to eliminate all of those unknowns and just be left with a ratio, right? A factor of how much the resistance changed. So you can look at how this example was worked out in the chapter. They, work it out a little bit differently than I did because they plug in the numbers, and so that may work for you better, okay? I was just kind of showing it to you in a little bit more abstract way to really illustrate the problem-solving technique, okay? Because once you start plugging in all these numbers, you spend time in your calculator and you can kind of like lose track of where you are. So that's why working algebraically, it's great because it can really show you the big picture of the problem without getting kind of tangled up in all the little numbers and plugging in numbers, okay? And you can see that it actually took a lot less time because I could do it all in my head, right? I didn't need to consult my calculator for anything. So this is just a problem-solving strategy. If you're not here yet, if this method does not make sense to you yet, that's totally okay, because this method will work too. It just may take a little longer. But it's good to look at both ways. So there's the answer, 5,000. So here's a question. Well, what's the current through those two wires if we hook it up to a 12-volt potential? So the resistance of wire 1 was 50. The resistance of wire 2 was 5,000. Our potential we're going to hook those wires up to is 12 volts. What's I? Well, that's easy, right? V equals IR. So if we solve for I, we're going to get V over R. And so then I1 will be equal to 12 over 50. And I2 will be equal to 12 over 5,000. And I don't actually have my calculator with me, so let's just peek at those values. So 12 over 50 is 0.24. Current units are amps, right? And so then this one will be 0.0024. If I did my math correctly, 0.0024. Yeah, 0.0024. That's 2.4 times 10 to the minus 3. Yep. In other words, milli, right? 10 to the minus 3 is a milli. So 2.4 milliamps. Here's some very common factors that we'll be using for current, because currents are typically really small. Pico is 10 to the minus 12. Micro is 10 to the minus 6. Nano, 10 to the minus 9. Milli, 10 to the minus 3. So let's take a look at this, got the concept. It looks like, okay, so we have a material, an unknown material. We apply different potential differences across the wire, and then we measure the resulting current. Here are the results. So we applied 2 volts, we applied 4 volts, and then we applied 8 volts. So we doubled the volts each time. The current read 0.15 for the first, 0.28 for the second, and 0.5 for the third. So can we tell if it's ohmic or not? So recall that ohmic follows V equals IR, or if you want to replace it, if you want to rearrange it, I equals 1 over R times V. If you want it in Y equals MX form, right? Either way, it's actually better if we just investigate it using V equals IR. So if this were to follow, if this object were to be ohmic, if we increase the voltage by a factor of 2, we should also expect to see a factor of 2 increase in the current. Okay, so do we see that? We increase the voltage by a factor of 2. Does this increase by a factor of 2? Not quite. Almost. Okay, so let's, because 0.15 times 2 is 30, is 0.3, which is almost 0.28. So let's look at the next one. We're going to increase again by a factor of 2. Does the current increase by a factor of 2? No. Now we can see it definitely doesn't, right? We're going from 0.28, a factor of 2 would be 0.6, and we're definitely nowhere near 0.6, it's 0.5. So this material is going to be non-ohmic because it is not scaling linearly, right? For every factor of 2 increase in V, I should get a factor of 2 increase in I. For every factor of 25 increase in potential, I should get a factor of 25 increase in I, right? That's what a proportional relationship means. So it's definitely not ohmic. You could also kind of plot it if you want to visualize it, right? It's hard because, you know, it's, let's see, this could be 2, 4, 8. It's hard because it's sort of like not exactly the scale. And let's make this be 0.1, 0.2, 0.3, 0.4, 0.5. Okay, if I go over 2 volts, I'm at 0.15. If I go over 4 volts, I'm at 0.3, a little bit under 0.3. And if I'm at 8, I'm at 0.5. So you can kind of see, right, a straight line. Let me draw a straight line. A straight line, right, it starts to deviate from the straight line. Of course, 2 points together will make a straight line, but you can tell that the third point is not on that line, so it's not ohmic. Graphically is not the best way, but I just wanted to kind of just keep showing you the graphs of this, because when you guys do your labs, you're going to be doing this. You're basically going to be doing exactly like this. This got the concept. So let's kind of wrap up this section. We introduced resistivity, and that's just a measure of how well or how poorly a material resists or inhibits current, okay? So if it inhibits it very well, then the resistivity will be high, right? Which means it doesn't allow current to pass very easily. If it inhibits it poorly, that means that there is not a lot of inhibition and the current is going to be high. So the value of resistivity, so it's important, the difference between resistivity and resistance is this is a material property, okay? It does not depend on dimensions of the object. This, however, resistance depends on the dimensions of the object, right? Because R equals rho L over A. And as we saw in got the concept earlier, that changing L changes A and thus changes R, okay? But resistivity, if we go back to that table, right? Resistivity is a tabled value for each material. So it's actually only changes with temperature. It doesn't change with what the dimensions of the material are. All right, this is just a tabulated value. So that's the difference between resistance and resistivity. So let's go on. Let's talk a little bit more about resistance and why it's important. And I think you're gonna like these two analogies or models of resistance in biology. But first, let's talk about resistors in a circuit, because we are going to be dealing with this. So these little guys are resistors, not the black things, but these guys are resistors, okay? They have little bands on them which tell you what the value of the resistance is and how well that value is known, to what degree. And resistors are everywhere. They are in your phone, they're in all electronic devices, okay? So they're there to change the current, that value that's flowing through the circuit, okay? That's really why we add resistors, is because we want to apply a certain voltage, but maybe we don't want the current to be super high, so we throw a resistor on there to decrease the current. So So the purpose of resistors is to change the current flowing through the circuit. So where can we see this kind of idea in biology? Well, in cell biology, we can model the ion exchange through cells with as little resistors. So basically, you have a cell. Inside the cell are potassium ions, okay? And they can't go through a membrane unless a channel opens up. So potassium channels are embedded in the membrane, and there are certain conditions that trigger them to open up. And when they do, these potassium, which are positive ions, are allowed to pass through. And so when they pass through, we change how much charge is in the cell, and then we're starting to change how much charge is outside the cell. Okay? So as more potassium ions start to flow out, we end up decreasing the charge inside the cell, increase the charge outside the cell. So we basically have a separation of charge over a distance. And that actually gives us a change in potential. So this potential is created that allows charges, right? Potentials give energy to charges, okay? So this potential is giving those charges enough energy to escape the cell. And when they reach a certain point, that potential will start to decrease and no longer provide enough energy to the charge to leave the cell. And when that happens, you are at equilibrium, and the membrane potential prevents any additional movement of the positively charged potassium ions out of the cell. Okay, so this potential is no longer large enough to give a sufficient amount of energy to the charge to leave the membrane, and that's the signal that the cell has finished doing its job and the cell is now in equilibrium. So we can model this as a little resistor, right? So the current flow would be the flow of the positive ions. The resistance of the membrane would be the channel's resistance. And then the potential would be the potential created by how many charges are on the outside and how many charges are on the inside of the cell. And so what's going on, the process that we're explaining with resistance and potential and electric field and current, the process that we are explaining is how a cell membrane reaches equilibrium. Okay, how it knows to stop pushing charges out of the cell. So you can kind of read through these slides. It's basically what I explained, right? It's a way to look at this method in which cells know when to stop doing a process. We can think of it as current being the flow of the positive ions, the cell membrane and the channels being resistors, okay? The potential that's created is created by the separation of charges between the outside of the cell and the inside of the cell, right? Kind of like the terminals of a battery. You have a positive terminal and a negative terminal. So you have a region of positive charges and a region of negative charges. So that separation creates a potential. Potentials give energy to charges to move. And once there's not enough energy, those charges are going to stop moving and the cell will have reached equilibrium. So there is a small, simple example related to this idea. So the question is, okay, that's great. Let's model those potassium channels as resistors. How do we like measure that and know these values? Well, there's an instrument called a patch clamp, and this patch clamp sticks onto a portion of the cell and measures the resistance of that channel. So the way we measure resistance, as I mentioned before, is we apply a particular voltage and we measure a current. And the slope of that graph, depending on which you're plotting on the y and which you're plotting on the x, will give you R. Okay, so, or 1 over R. So here are some values that we got. In the experiment, we've applied 0.12 volts across the patch. And then we measured 6.6 picoamps of current. What is the resistance of this channel? So we can use V equals IR to figure that out. We're solving for R, so we're going to do V over I. And that's going to give us, we'll look for the number. I didn't bring my calculator. 1.82 times 10 to the 10. A gigantic resistance. So you may be wondering, okay, well, with such a gigantic resistance, how in the world are these ions even leaving the cell, right? Well, remember, resistance has geometrical factors associated with it. And we all know cells are really small. One portion of the membrane, right? One channel is going to be even smaller. So with a really small cross-sectional area of that channel, like on the order of nanometers or angstroms, you are going to get a gigantic resistance, right? If this is small, super small, then this is going to be super big. So I think a better way to understand what the actual, that's why we need resistivity, right? Because resistance can be misleading because there are geometrical factors that influence the resistance to the current. And it can kind of obscure what's actually happened. You may look at this and you'd be like, well, there's no way in heck those potassium ions can get through that gigantic number of, of ohms, right? So if we look at the resistivity, however, the resistivity is not affected by the geometry of the problem. And we can find the resistivity if we know the dimensions of L and A and if we know R. So I believe this problem, it may not tell us the resistivity, but it does tell us why that number is so big. It's because look at the thickness of the cell membrane. It's 7.5 nanometers. So 7.5 nanometers is very, very small. And it's, of course, going to change and make the resistance really high. So in this second application, I'm going to let you guys review it on your own. I'm not going to test on it or anything like that. It's just we have to, we can't talk about every single thing in this. We'd be talking for 3 weeks on just a couple of chapters. So I have to cut some stuff out, although this is very interesting. So this gets into kind of neurobiology and how the brain works. So how the brain works, well, you might already know this. The brain communicates with other regions of the brain through electrical signals, right? Electrical signals are ions, either potassium or calcium channels, right? There's a whole bunch of ions of atomic elements in your brain, and they move around and create currents. So read through this if you kind of want to get to know how these parameters that we're learning about in this chapter relate to neurology and neurobiology. So this example kind of goes along with that. It's not going to be on the exam or anything, so that'll just be extra if you want to do that. But what I do want to cover is another kind of relationship problem. Okay, it's kind of similar to the one before. Got to read it very carefully. You've seen the answer already, but let's work it out together. So we have two copper wires. Their length is the same this time. But the only thing that's changing is the diameter. So compared to the smaller diameter wire, the wire that has a larger diameter would have a resistance of what? Okay, so we're looking at the larger diameter wire again. So let's kind of draw our picture out. So we have a small diameter wire, we have a larger one. Okay, they're the same length. And let's look at this. So the diameter is 4 times. So this one is basically D1, no, D2 is 4 times D1, right? The diameter of 2 is 4 times D1. It's bigger. This doesn't look too much bigger. Let me kind of make this one look smaller. There we go. So, so these kind of are our constraints for the problem, and we're going to compare the resistance of the bigger to the smaller. So we're going to put the resistance of the larger one on top. Okay, and let's write down real quick what the resistance equation is. It's rho L over A, right? So R2 is going to be rho, no subscript for L since they're equal, over A1. I'm sorry, A2. Okay, he's in the numerator. We're going to divide that by rho L over A1, which is in the denominator. And just to clean it up, I'm going to write that as the reciprocal. And when I do that, I can clearly see some cancellations. So what I end up with is the ratio of R1 to R2 is equal to the ratio of A1 over A2. So what's A1 and A2? Well, they are the cross-sectional area of the wire, which is a circle. So that's going to be pi. It's normally the area of a circle is pi r squared, but since we're dealing with diameter, I'm going to change that r to d over 2. Okay, so we have pi d1 over 2 squared. Pi, now this would be d2 over 2 squared, but what is d2? D2 is 4 times D1. I can plug that in. And then we got some cancellations going on here, right? And what we end up with is that R2 over R1 is equal to D1 squared over 4D1 squared, which is D1 squared over 16D1 squared. The D1s go away, and that leaves me with 1 over 16. So if I move this R1 over here to complete my sentence, right, R2 is 1/16 of R1. So the resistance of the larger wire is 1/16 of the resistance of the smaller wire. And let's check if that makes sense, right? So what are we changing here? We're increasing the cross-sectional area. So since cross-sectional area is in the denominator, we do expect R to decrease. So one of these two would be the correct answer, and going through this math here shows us that the correct answer is 1 over 16 and not 1 over 4. And you can kind of like work that on your head because the radius or the diameter, right, those are squared terms in the cross-sectional area. So you would imagine that, you know, it's a squared term so that it should be a more significant change. So let's review what we talked about so far, right? Resistance, we defined resistivity, and we kind of saw them applied in physiology of cells, okay? Cell biology. So the other thing that we saw was that if the relationship V equals IR, right? So if we increase the potential, we're going to increase the amount of current running through the circuit, and that is going to be scaled by the resistance R. So, which should remain constant. So that means if we increase the voltage by a factor of 2, then we should also see a factor of 2 increase in the current.